In Lecture 2, we'll spend some time learning how to balance redox reactions. Well, in reality, there's no real fundamental difference between balancing a redox reaction and balancing any other chemical reaction. Ultimately, you want the number of atoms of each element to be equal on both sides of the equation. That would be the mass balance, and the total charges on any ions to add up to the same sign and magnitude on both sides of the equation. In other words, charge balance. So why would we single out redox reactions for special consideration? Well, the first reason is that it's not unusual for redox reactions to be fairly complex, making simultaneous mass and charge balance challenging. And the ability to track electron transfer by assignment of oxidation numbers, and the fact that the total number of electrons lost must equal the number gained, gives us a tool to deal with this often encountered complexity. Now, in the previous lecture, we assigned oxidation numbers in this balanced redox reaction listed below, which involved the oxidation of chloride ions by dichromate. We can highlight both the mass and the charge balance below the equation. So what I'm going to do here is show you why this is balanced by showing you that it's balanced according to mass and charge. So we'll look at the mass balance, we'll look at the charge balance, and of course by balance we mean the same on the left and on the right of the arrow. So for the mass balance, we have 14 hydrogens on the left. Yes, I know they're in the form of hydrogen ions, but I'm just counting the element symbol, 14 H's. And on the right, there's 14 H's here stowed away here in the 7 water molecules. There's 2 chromiums on the left. There's 2 chromiums on the right. There are 7 oxygens on the left. There's 7 oxygens on the right. There's 6 chlorines on the left. There's 6 chlorines on the right. So yes, this equation is balanced according to mass, as it should be because we said the equation was balanced. Now let's look at the charge balance. We have 14 plus 1 charges on the left, plus a minus 2 charge from this single chromate ion, and then we have 6 negative 1 charges from the chloride ions. And so on the left, the total charge on this reactant side is plus 6. Notice it doesn't have to be 0, we just need to know what it is. And now we need to see if it's matched on the right. Well, on the right we have 2 chromium 3 plus ions, water is neutral, chlorine in its elemental form is neutral, so therefore we have a total charge on the product side of plus 6, so the charge balance is okay. So this redox reaction is balanced according to mass and charge, as it should be. Well, what was so special about how someone went and balanced this equation and gave us these coefficients? What we're going to do is look at how reactions like this are typically balanced and how the questions involving these balancing the balancing of these reactions are typically phrased in general chemistry textbooks. So this would be not an uncommon way to see a question involving balancing or getting this balanced equation, and that would be complete and balance the following redox reaction in acid solution. Dichromate plus chloride going to chromium 3 plus and chlorine the element. So clearly this is not balanced now. And the question that you would very typically see would be something like this, expecting you to arrive at a complete balanced equation like the one we wrote up here that's balanced according to mass and charge. So in order to balance this, we have several tasks that we'd need to complete. The first would be the mass balance. The second would be the charge balance. We have to deal with what's meant by in acid solution. We're assuming that we're going to have to introduce hydrogen ions somewhere because they are in the final equation, but they're not given in the question. And the other thing to ask is, where did H2O come from in the balanced equation? Because it certainly doesn't show up in the question. Well, we can take care of all these challenges by first assigning oxidation numbers, which we said in the previous lecture was important, and then clearly identifying what is being oxidized and what's being reduced. Once we do that, we follow a protocol to get our final balanced equation. So let's try to balance this equation and come back to the answer that we already know. So here's our question. First thing we want to do is assign oxidation numbers to each atom and identify what is oxidized and what's reduced. Well, of course, on the left, each oxygen would be -2, each chromium is +6, each chloride is -1. Now remember, we're just assigning oxidation numbers using the guidelines and the reasoning outlined in the first lecture. Oxidation number of chromium 3+ would be +3. The oxidation number of elemental chlorine is 0. So we see right away that it appears to be chromium that's reduced and chloride that's oxidized in this reaction. So now that we've done that, we're going to split this reaction into two so-called half reactions. One half reaction showing the oxidation and the other showing the reduction. So let's do that. The oxidation half reaction would be the part of the reaction involving oxidation, which would be chloride going to chlorine. So I'm just going to write that right here. And I know this isn't balanced, but I'm just dragging it out of our starting equation and writing it here because it represents an oxidation. And the reduction involves not just chromium, of course, but chromium attached to oxygen in the chromate ion, ending up as just chromium 3+. Again, this is wildly not balanced, but again, I'm just dragging the reduction part of this equation down here and calling it the reduction half reaction. Now what we're going to do is separately treat each half reaction and get each half reaction balanced. The first thing we're going to do is balance each half reaction according to the number of atoms. In other words, do a mass balance. You already see that there could be a problem because in the reduction half reaction, how are we going to balance this when oxygen's completely disappeared from the right side of the arrow? Well, if oxygen atoms are required, you add them in the form of water molecules. And if H atoms are required, you add them in the form of H+ ions. Remember, we said this balanced redox reaction is occurring in acidic solution. So it makes sense that if we need hydrogens, it wouldn't be at least unreasonable to assume we could add hydrogen ions. So let's do that, and the changes will appear in pink here. So for the oxidation half reaction, we only need to put a 2 in front of the chloride, and now this equation is balanced according to mass, numbers of atoms on each side. For the reduction half reaction, I'll give ourselves a little room and say that we certainly need 2 chromiums on the right to balance the chromiums on the left. We'll take care of the oxygen problem by adding 7 waters on the right. That gives us a deficit of hydrogens on the left, so we'll add hydrogens on the left by adding them in the form of hydrogen ions. So we've taken care of introducing 7 oxygens on the right, and then we've taken care of the new problem we introduced here by having 14 hydrogens suddenly appear, but we'll put them on the left as hydrogen ions to balance the hydrogens. So we've now balanced each half reaction separately according to the numbers of atoms of each side. We've done a mass balance. Well, this is where we left off from the previous slide. The changes that were in pink now are no longer in pink because we've accepted them. Now we'll move on to separately balance each half reaction according to charge. In other words, we'll do a charge balance. The trick here is that this needs to be done by adding electrons to either the reactant or the product side. So you're restricted to trying to take care of the charge balance by only adding electrons to one side or the other. Well, let's do that. For the oxidation half reaction, we can take care of the charge balance by adding 2 electrons to the right-hand side. See, we have 2 minus charges on the left. We had neutral on the right. We're going to put a -2 total charge on the right by just adding 2 electrons. Now, this oxidation half reaction is balanced according to charge. How about the reduction half reaction? Well, we can take care of the charge problem here by adding 6 electrons to the left of the arrow, because now this half reaction will be balanced according to charge, because we'd have 14 H pluses, a 2 minus, that would leave a plus 12 charge. 6 minuses would leave a plus 6. On the right of the arrow, plus 6. So we've taken care of the charge balance in the reduction half reaction. Now, if necessary, you need to multiply one or both of the half reactions by an integer factor with the goal of making the number of electrons lost in the oxidation half reaction equal to the number of electrons gained in the reduction half reaction. Remember, electrons are conserved in redox reactions. So we split up the reaction into 2 half reactions. We've balanced each half reaction separately according to mass and charge. Now our final task is to get the number of electrons lost in the oxidation half reaction, equal to the number gained in the reduction half reaction. Now we can do that here by simply multiplying the oxidation half reaction through by a factor of 3. So let's do that. If we multiply it through by 3, we'd get 6 chlorides going to 3 chlorine atoms, 3 chlorine molecules, plus 6 electrons. We now write the reduction half reaction underneath that. And now you'll see that the number of electrons lost in the oxidation half reaction equals the number gained in the reduction half reaction. What do we do now? Well, we just need to add these 2 half reactions back together. So we'll do that and we'll add up all of the terms on the left of the arrows. So we have 6 chlorides, 14 hydrogen ions, a dichromate ion, and 6 electrons going to 3 chlorine molecules plus 6 electrons plus 2 chromium 3 plus ions plus 7 waters. We can now look for things to cancel, and you can see that there's 6 electrons on either side of the arrow, so we can cancel those out. And it wouldn't be uncommon to find some other things to cancel out. However, in this particular reaction, there are no additional items to cancel besides the electrons, so we can rewrite the equation and perform a final mass balance and charge balance check. So for the mass balance, we have 6 chlorines on the left and on the right, 14 hydrogens on the left and on the right. We have 2 chromiums on the left and on the right. We have 7 oxygens on the left and on the right, so the mass balance is okay. The charge balance, we have 6 times a -1 on the left, plus 14 times +1, plus a -2 gives +6. And on the right, we have 3 times 0, plus 2 times a +3, plus 7 times 0 gives +6. So the charge balance is okay. You might ask, why do we need to do this final check? I guess the best answer is sometimes mistakes are made. So this is a final check to make sure that your overall redox reaction is balanced. Now, the presence of hydrogen ions and H2O in the balanced equation reminds us that this redox reaction occurred in acidic solution, so we were asked to balance it in acidic solution. Now, a redox reaction can also be balanced in a basic solution, but we don't have to do anything really new. We just have to do one more step for a basic solution. So the general wisdom here is that for a basic solution, you just first carry out steps assuming the reaction is in acidic solution. Then at the end, you fix the balanced equation by adding hydroxide ions to both sides of the reaction to react with any hydrogen ions. This forms water. And then when you do that, some additional simplifications sometimes are necessary. So here's the redox reaction we just finished balancing in acidic solution on the previous slide. Let's suppose the original question said, balance this reaction in basic solution. Well, what you would have done, or what I would suggest you do, is balance it in acidic solution. You'd arrive at this answer, and then you'd say, well, look, we need to get rid of the hydrogen ions, so I'm going to add 14 hydroxides to the left to get rid of the hydrogen ions. And since this is a chemical equation, you're going to need to add those 14 hydroxide ions to the right side as well. So let's add our hydroxides to the left. When we do that, they'll react with the 14 hydrogen ions and form 14 waters. And then we also add the 14 hydroxides to the right. You'll notice that we'll now have some waters to cancel out. But let's write the equation now as it appears. We have the 14 hydroxides and 14 hydrogen ions going to 14 waters on the left of the arrow. We fill everything else in that's supposed to be there. On the right of the arrow, we have what we had before, but now we also have 14 hydroxides. You'll notice there's water on both sides of the equation, so we can get rid of 7 on the right and leave 7 on the left. So we can rewrite the equation now, and then it's now a redox reaction in basic solution. Let's recheck for mass and charge balance to make sure this really is balanced. For the mass balance, we have 6 chlorines on the left, 6 on the right. We have 14 hydrogens on the left. We have 14 on the right. We have 2 chromiums on the left. We have 2 chromiums on the right. We have 14 oxygens on the left. And you say, where did they come from? Well, it would be 7 from the water and 7 from the dichromate ion. And we have 14 oxygens on the right. So this equation appears to be balanced according to mass. For the charge balance, we have 6 times a minus 1 on the left, plus 0 from the waters. I guess I could have written 7 times 0, plus a minus 2, and that adds up there to a minus 8. And on the right, we'd have 0 from the 3 chlorines. We'd have 2 times a plus 3 from the chromium 3 plus, and then we have 14 negative 1s. So in total, we have a minus 8 on the right. So the charge balance is okay. So this reaction is now balanced in basic solution. So the presence of hydroxide and water in the balanced equation reminds us that this redox reaction occurred in basic solution. So let's summarize to this point. The balanced equations for the oxidation of chloride by dichromate are listed as in acidic solution, it looks like this. In basic solution, it looks like this. And you might ask, what's the point? Well, redox reactions taking place in aqueous solution are often pH dependent. Now, a skeptic would claim that there's no real difference in the above two redox reactions, since both seem to involve the oxidation of chloride to chlorine gas and dichromate ions to chromium 3+ ions, regardless of the pH, whether the pH is low as in acidic solutions or high in basic solutions. However, we will soon discover that the spontaneity of a redox reaction, in other words, the actual value of the delta G for the reaction, can be strongly affected by pH. And in fact, in some cases, the pH controls the actual product distribution. So here's an example. Many biochemically important reactions are actually pH dependent. Here's an example. The half reaction representing the reduction of oxygen to water is an important energy producing reaction in living systems. Remember, you breathe oxygen. The reaction involves not only electron transfer, but also hydrogen ions, which makes the reaction pH dependent. So at lower pH values, where hydrogen ions are plentiful, the reaction can be written as oxygen plus 4 electrons plus 4 hydrogen ions, making 2 water molecules. And the delta G for this reaction is minus 470 kilojoules per mole, which is ridiculously negative, which means it's ridiculously spontaneous. Now at higher pH values, where the H+ concentration would be low and the OH- concentration would be high, this same reduction of oxygen can be written as oxygen plus 4 electrons plus 2 waters going to 4 hydroxides. And the delta G for this reaction, while still negative, is much less negative than it is in acidic solution. So here the pH affects not only the free energy change, the spontaneity of the reaction, but it actually changes or affects the nature of the products. So in acidic solution, the product of the reduction of oxygen is water. In basic solution, the product of the reduction of oxygen are hydroxide ions. So interestingly, the pH dependence of biochemical reactions becomes much more complex than this due to the necessity to create H+ concentration gradients across membranes surrounding important cellular components. For now, though, we're going to do a few more examples in the next part of this lecture of balancing redox reactions.